$135 million. And the key bullet on this particular slide is the 1,200 people, the feet on the street that Chesterton provides to our end user customers. We're a leader in fluid sealing solutions and equipment and infrastructure protection. Chesterton is known for our award-winning pump and valve sealing solutions and services, as well as industrial lubrication and industrial wear protection products. The second bullet there is really key. We're a company with a strong commitment to innovation, helping our customers with products and programs that help them operate more reliably, efficiently, and economically. Chesterton's tradition throughout its history has been working with end-user customers in developing new technologies and new solutions to make their plants and operations run more reliably, efficiently, and economically. So today we're going to be talking about environmental control plans for seals in the water and wastewater industry. We're going to talk about their purpose, their origins and designations. We're going to talk about the most commonly used control plans in the water and wastewater industries today. We're going to talk about some of the associated costs when we utilize environmental control systems. And we're going to talk about how we can mitigate some of those costs without impacting or hopefully improving seal performance. So what are environmental controls and what are they used for? It's commonly known that the failure of the mechanical seal is one of the leading causes of pump downtime. There are a variety of reasons that a seal may fail in operation, and one of those can be due to the environmental controls. Extended seal life and harsher applications is partly a function of being able to control the environment around the seal. So essentially, environmental controls are strategies that are used to control the temperature, pressure, and fluid within the seal chamber, or more commonly referred to as the stuffing box. The goal of environmental controls is to provide clean and cool seal face lubrication and effective heat removal. Don't want to oversimplify the issue at all, but basically, if you talk to most mechanical seal manufacturers, what they'll tell you is the two things that'll kill a seal are heat and dirt. Dirt and solids that you might find within the fluid that's being pumped itself. It could also be the temperature associated with the fluid itself. But there is also heat that's generated between the rotating and stationary seal faces of mechanical seal that generates significant heat. In fact, we require a thin film of lubrication between those seal faces to provide a cool face lubrication. So we want to have these environmental controls that are going to provide that clean and cool environment with which the seal can work. In terms of what's called the API piping plans for environmental controls, the American Petroleum Institute established standardized piping plans or environmental control plans for seals based on the seal arrangements that are used, the fluids that are being pumped, and the control equipment that's associated with the mechanical sealing system. Generally, the piping plans are assigned a two-digit designation, for example, Plan 01 or Plan 11. There are actually close to 25 piping plans that are published, including some variants. ANSI also has a comparable set of piping plans, but they're with a 4-digit configuration. But like the API, they also use the 0111, but they put a 73 in front of it. So it's 7301 or 7311. In terms of environmental controls common to water and wastewater, majority of the pumping applications in a water or wastewater system can effectively be sealed by a single seal configuration. So today we're going to focus primarily on the single seal controls, along with a select dual seal system. The first plan we're going to look at is Plan O2, or a dead-ended seal chamber or a stuffing box. So there's no internal recirculation of pump fluid. It strictly comes in through the throat of the stuffing box, but there's no flush, if you will, from an outside source. In many instances, not so much in the water and wastewater industry, but it's used in conjunction with a cooling jacket. And that cooling jacket is here, okay? And that's used, excuse me, that's used to cool or heat process fluid to promote flow in and around the seal. So we want to, once again, have a cool, clean environment within the seal chamber. But more times than not, it's commonly used with only cool, clean pump fluids like water, which we'll find in this industry. The second piping plan that we're going to talk about is Plan 11, known as Discharge Recirculation. It's one of the most common piping plans used throughout all the industries, and it's used primarily with clean fluids. What we do is we take a discharge from the discharge of the pump, and we recirculate it through an orifice to the seal flush port, and we introduce that into the seal chamber. Ideally, what we're trying to do here is provide that, once again, that more favorable seal environment. This particular piping plan is used to control discharge. We use an orifice to control the discharge pressure to the seal, but it's used to prevent, to raise pressure in the seal chamber and to prevent flashing in and around those seal faces. And we want to lower the temperature at the seal faces. Many times we use it in conjunction with a close clearance bushing here at the bottom of the stuffing box to generate a back pressure within that sealed chamber. The next plan we're going to talk about is a Plan 12. This is a discharge recirculation with a strainer. And it's similar to a Plan 11, but with a strainer inline, or a Y strainer, to remove solids from discharge and recirculation. And what we're trying to accomplish here is, if there are solids in the pump fluid and they're coming through that discharge line into the sealed chamber, we don't want to have any solids that might be in that fluid. We don't want them to be doing damage to the seal faces themselves. So we use a strainer to capture those solids. But you have to use them with caution. Strainers are prone to clogging, so periodic inspection is required. I've seen this quite often in return-activated sludge and waste-activated sludge applications when there wasn't a clean flush available to them, or they did not want to use a clean flush from an external source. So they used the discharge recirculation and they strained out the solids. But once again, they should be used with caution because the strainers can be clogged. So periodic inspection is required. The next piping plan is Plan 13, which is called suction recirculation. And this is commonly used and highly recommended for vertical pumps. And if you take nothing away from this, this webinar today, I think this would probably be one tidbit to hold on to. And that is, in any vertical pump application, you always want to make sure that a Plan 13 is specified. It vents air to prevent dry running of the seal. If we notice in the drawing itself, the mechanical seal is situated at the highest end of the wet end of the pump. As the pump is flooded, air can be trapped in there. So we want to vent that air away. And we're going to be talking about this piping plan a little bit more detail, in a little bit more detail in a few slides from now. It's also to remove solids from the chamber. Once again, we want a clean environment for those mechanical seal faces wherever possible. It also lowers pressure in the seal chamber. Plan 14 is a suction and discharge recirculation piping plan, and that's also used with vertical pumps. And it's a combination of a Plan 11 and a 13 to promote flow through the seal chamber for cooling, while also venting the seal chamber and lowering pressure. And it ensures product recirculation. We see this a lot in hot applications of those that are trained with air. So you might see that in water and wastewater and vertical applications, mostly to deal with the entrained air potential. Plan 31 is a discharge recirculation with the cyclone separator. Okay, so we take the fluid from the discharge of the pump and we take it through a separator which removes solids from the fluid and directs them, and I apologize, not to solids but back to the suction of the pump. And this is utilized once again when clean flush is not available, or we don't want to dilute the product with a clean flush. So we utilize the pump fluid itself. We just want to remove the solids that could be entrained in the fluid itself, the pump fluid. What we're trying to do is recirculate clean product and to remove that frictional seal face heat. Okay. At any time pressure increase in the stuffing box is desired, this is a common piping plan that is used. The next one, Plan 32, clean flush. And this is probably the most common piping plan utilized in water and wastewater. And what we do is we provide clean flush to the seal, generally speaking at 15 psi over the stuffing box pressure to cool and lubricate the seal faces. And we use that, and we use it in conjunction with a close clearance bushing here again. Once again, we're trying to generate a back pressure within the stuffing box, and we're changing the game. We're not trying to seal the pump fluid anymore. We're introducing flow into the stuffing box with the clean fluid, and essentially what we're doing is we're now sealing the clean fluid as opposed to the pump product, which could have solids entrained within it. We use it in conjunction with that close clearance bushing, but in addition to that, we utilize a flow meter to regulate the amount of flush water being utilized, a pressure gauge so we can manage the pressure, and once again we want it at 15 to let's say 20 psi over the stuffing box pressure, as well as a check valve. Plan 54 is a pressurized barrier fluid circulation from an external source. I like to call this a Plan 32 for dual seals. And essentially we're bringing in this clean fluid from an outside source, and we're injecting it into the seal between the inboard seal of a dual seal and the outboard seal. And we do that at a greater pressure, 15 to 30 psi over the maximum seal chamber pressure. And what we're doing is we're providing that clean fluid between the seal faces, both inboard and outboard. In many instances, used with devices that regulates the pressure and the flow, as well as in some instances provides some means of an inboard seal leak detection device. In water and wastewater treatment, in terms of environmental controls, what we're trying to do is we're trying to control the fluid properties and remove trapped air. They are the most significant concerns for us. By doing so, we prevent solids from building up in the seal chamber. We keep abrasives away from the seal faces, and we prevent heat generation at the seal faces. Once again, we want a thin film of fluid migrating between the rotating and stationary seal faces to provide lubrication to those seal faces. Without that lubrication, they would run dry, they would generate a significant amount of heat, doing damage to the seal faces themselves, And some of the secondary seals, like O-rings, that are generally found in a mechanical seal. And they would actually melt those secondary seals and cause a mechanical seal to fail. So, in terms of environmental controls in water and wastewater, we're going to focus on Plan 32, the clean flush, which is the most prevalent environmental control. And we want to talk about, in particular, Plan 13, suction recirculation, which, by the way, I find is one of the most underspecified piping plans utilized in water and wastewater. In many instances, we see specifications in a vertical pump application in which no environmental control is specified for the mechanical seal. So it's underspecified, and it can do a significant amount of damage to the seal itself. We'll talk about that a little bit here. In a vertical pump, when flooding it, what happens is, as the fluid rises within the seal chamber, there's a pocket of air which can be trapped at the top. Once again, the seal sitting at the top end of the wet end of the pump, and that air bubble can be trapped there. If the pump is turned on, the seal is not running in a wet environment, and those seal faces are not lubricated. So that causes significant damage to the seal faces themselves and to the seal. So what we want to do is we want to vent that air utilizing the Plan 13 back to suction of the pump or to the sump of the pump itself. So we allow water to rise, the fluid to rise within the seal chamber, so the seal is now running in a wet environment and we're getting seal face lubrication. Once again, this is probably one of the most common concerns that we have within the mechanical seal industry in terms of having adequate seal face lubrication. And unfortunately, it's probably one of the most underspecified environmental control plans. And on startup of a pump, we get significant damage and ultimate seal failure in a relatively short period of time. Once again, the most common single seal environmental control that's used in the water and wastewater industry is called a flush, or Plan 32. It's a clean, cool fluid with a restriction bushing in the seal chamber to create a flow. The strategy being we're trying to prevent solids building up in the stuffing box. We want to have a certain flow underneath that throat bushing in the seal chamber, okay, around 15 feet per second. So what we're doing is we've changed the game. A pump fluid that may have solids entrained in it is pushed out of the stuffing box. And now instead of sealing that solids-laden fluid, we're now sealing the cool, clean flush water. So we're trying to keep those abrasives away from the seal faces. And we're also trying to push out air out of the stuffing box. At the same time, we're forcing a lubrication across those seal faces. So what are our sources of flush water? Typically, they're city water or plant effluent. But there are some issues associated with flush water. The capital costs of designing in a flush water system that's going to run to the numerous pumps in a capital project, for example. There's significant costs associated with that. There's also the reliability of flush water systems. In my years of doing business in this industry, one millwright said to me at one point, if there's a valve to be turned off, sooner or later it will be turned off. And if it has anything to do with a flush water system, it could result in the loss of many mechanical seals to multiple pumps. In terms of quality of flush, generally speaking, if we're using city water, that's not a concern. Also with plant effluent, typically that's not a concern as well, but there are indeed some amounts of minute solids in plant effluent which we should concern ourselves with. But generally speaking, the quality of flush is not a concern here in the water and wastewater industry as you might, let's say, find in mining industries and heavy-duty flushes. But the issues associated using with city water as a flush is the cost associated with it. A typical cost for flush is about $0.002 per gallon. If we use a pump with a shaft size of about 2 inches, there's a rule of thumb that's used throughout the industry in terms of flush water rate. We generally use between 3/4 to 1 gallon per inch of shaft size. So if we use 3/4 of an inch as our GPM for this particular example, for a 2-inch shaft size, our typical flush rate would be 1.5 gallons per minute per pump. So if we do the math, and that 0.002 times 1.5 gallons per minute times 60 minutes times 24 hours a day times 365 days a year, for one pump, the cost at that amount, that cost would be $1,576 for one pump. So within a treatment plant, for example, how many pumps are being flushed? In fact, how many pumps have shaft sizes in excess of 2 inches? So as we increase the shaft size of a given pump, the amount of flush water that's required also has to go up. So the cost can be very, very significant. And I just got a little blurb there in the parentheses. The cost of water per gallon in New York City, for example, is $0.005 dollars per gallon. So the cost can be very, very significant in using city water. Okay, so what about plant effluent as flush? Well, the issue to that is that it does cost a certain amount to treat a gallon of wastewater. Typical cost to ratepayers within a particular municipality is $0.003 per gallon. So if we use our pump shaft size again, of being around 2 inches, and we use our 3/4 of a gallon per minute per inch of shaft size, we would have that flush rate of 1.5 gallons per minute. So we once again do the math, look at the costs associated with one pump. And once again, we ask those questions. How many pumps are in fact being flushed? How many pumps have shaft sizes in excess of 2 inches? So we've got a little bit of a flush water dilemma. To flush or not to flush? Why do we use flush water? We want to provide an optimal environment within it which a seal can operate. We want to push out those solids we were talking about that could potentially damage seal faces. And we want to push out air trapped in the seal chamber that can cause heat. So what we do we use flush water to increase the seal pump reliability, to mitigate the #1 cause of unscheduled pump shutdowns, mechanical seal failure. We want to provide a cool, clean environment, but we know that there are costs associated with it. So why wouldn't we use flush water? Well, we talked about the capital costs of associating a flush water system into a plant design. We've also talked about the cost of city water or plant effluent. In fact, one of the processes within a wastewater treatment plant, for example, is a solids treatment element. And there the goal is to remove as much water out of the system as possible. So utilizing flush puts water back into that solids treatment aspect of the treatment plant. So it's counterproductive. So we'd like not to use flush water as much as possible, or in many ways, reduce it as best we possibly can. One of the strategies that are used to reduce or eliminate flush is utilizing what's called active throat pushing technology. Active throat pushings are used to reduce or eliminate flush fluid required and further enhance seal reliability by driving seal cavity circulation and exchange. That's a mouthful. Basically, what we're talking about here is the fluid from the pump fluid with solids entrained enters into the stuffing box. When the pump is turned on, the heavier particles, the solids, are thrown to the stuffing box bore, and they move along that stuffing box bore. Utilizing an active throat bushing with a spiral groove in it, the solids are then captured within those grooves and they are thrown back into the pumpage. So essentially the seal is running in a relatively clean environment. So if we're looking at a standard pump, once again, here is our mechanical seal. And what you see here is the cast-in throat that is found in a majority of pumps that are utilized. And basically that cast-in throat was used as kind of like a backstop when mechanical packing is used. Okay? And that's found in most stuffing boxes. What we do is, for a new pump, for example, we would have the pump manufacturer remove this throat, opening up that stuffing box. I want to talk a little bit and give you a little pictorial video demonstration of what happens when we have air trapped in the stuffing box. That's utilizing when we have that cast-in throat bushing. When the pump is being flooded, and you see the water rising here, that cast-in throat can actually act as a dam. Okay? And as you see the fluid rising, it comes to the top of the bottom of that cast-in throat, and an air pocket is captured within the stuffing box. We move on to the next video. You'll see that when we turn on that pump, second. Once again, the heavier element within the stuffing box is the fluid. That's thrown to the bore, but look where the air bubbles go, in and around the mechanical seal. So our seal faces are not running in the optimum environment. So that's public enemy number one for mechanical seals: heat that can be generated because there's no fluid lubrication of those seal faces. If we use active throat bushing technology, what we do is we machine out that throat cast in the bottom of the box, and this is the active throat bushing here. And there's a notch machined in at the 12 o'clock position that acts as a vent. So when we flood that stuffing box, the air has an opportunity to leave the stuffing box, and our seal is now running in a completely fluid environment. The second public enemy, if you will, public enemy number two for mechanical seals, are dirt. Okay? And this is a typical stuffing box without any environmental controls utilized. So you see the solids banging around those seal faces, possibly doing damage to the seal faces. The minute particles in the entrained solids are actually migrating across those faces, potentially doing damage. So what do? Historically, we've used flush water to push those solids out of the stuffing box. But we've talked about the costs associated with the flush fluids. So we can utilize active throat bushing technology to remove those particles from the seal chamber so the seal can be running in a clean environment. If we bring up the next one. So once the pump is turned on, you see the heavier particles, the solids, are thrown to the bore of the box, and they move towards the throat bushing, and they're captured within the spiral grooves. With a matter of seconds, you'll see that the particles in the stuffing box itself have been eliminated and gone out through the stuffing box, through the spiral grooves rather, and back into the pumpage itself. So now our seal is running in a clean, cool environment. And we do it with either reduced or eliminated flush. Now, in this particular instance, we've used it without any flush water whatsoever. There are limitations to when we can go flush-free, and we'd like to recommend no more than 6% solids in the stuffing box. But even when there is 6% solids, what we can generally do is use the active throat pushing technology in conjunction with the flush, but we can reduce that flush significantly to where we talk about flush water in terms of gallons per minute. With active throat pushing technology, we can reduce that to gallons per hour. And I go back to that comment that was made by one plant operator who said, if there's a valve to be turned off, it will be turned off. And if it's in regards to a flush water system, in the past, without active throat pushing technology, if you did that, we would now have no environmental controls within the seal chamber, and the seal would be running in a rather dirty environment, potentially doing damage. With active throat pushing technology and a reduced amount of flush, even if we were to lose that flush for a period of time, the active throat pushing would remove those solids and our seal would be able to run effectively. Jump by these slides for 1 second. So in summary, we've talked about the purpose of environmental controls for mechanical seals. We've talked about the API piping plans and how they were, what the designations and the origins were for the piping plans. We've talked about the common piping plans used in water and wastewater. We've talked about Plan 13 for vertical pumps, and they're critical for venting the seal chamber and preventing dry running seals. We've talked about Plan 32 flush, which is the most common environmental control that's used to remove solids and air in the seal chamber. But we have to balance that effort in terms of the cost of flush, in terms of the flow rates for seals, in terms of city water and plant effluent. And we've talked about the means of reducing or eliminating flush. We have a question from one of the participants. Can grease be used in place of water? Typically, you're going to find grease with packing, not so much in for mechanical seals. Todd. We have another question. Oops, that was a connection issue. Is active throat pushing a new name for this product? There is a trade name for the product. It's called Spiral Track. That's Chesterton's active throat pushing. But the generic name for the technology itself is called active throat pushing technology. Hope that answers your question, Todd. Are there any other questions?
All right, I'm going to give you guys some time to think about questions and go over a few other tidbits. We're going to have a survey to help us better this program and future programs. The link will appear right in the chat box, and it will take less than a minute. So if you could give us some feedback, it would help our program. I want to thank everybody for attending. I hope you gained some helpful insight. Remember to sign up for our next Water and Wastewater Solutions webinar, The Challenges of Wastewater Structural Degradation and Mitigation Strategies. That's also a mouthful. That one will be presented by Steve Bowditch, who is an industry expert and ARC product manager. And that's presenting on September 9th. We'll be sending out the presentation for if anybody missed a few of the earlier slides. We'll be sending out the recording. and we'll send out other helpful materials. If anybody has any other questions or needs information, Paul's information will be on that email. And as always, you can also reach out to myself for any questions.
I just want to interject. We covered a lot of ground in a short period of time. One recommendation I would make is in either upgrading existing pump and sealing systems, or in the specifications, for example, in a new plant or a new sealing, pumping or sealing system, then I recommend that you contact a sealing specialist to review the environmental controls that might be necessary for a given application, so we can reduce or eliminate flush water wherever possible. Once again, one comment I made during the presentation was with respect to vertical pumping applications, which are quite common within the industry, and one of the major causes of mechanical seal failure is the lack of a venting process to remove air from the seal chamber. That is something that really needs to be specified. So API Plan 13, as I mentioned earlier, if you take nothing away from this webinar, please jot that one down. And once again, I would highly recommend contacting your local seal specialist to review any pumping and sealing applications, so you can get the best bang for your buck out of the mechanical seals that are put into those systems. So thank you very much. Once again, if you can help us out by clicking on the survey and providing some feedback. And Christine, if there's anything else?
We'll leave the link up for a few minutes, and we'll also send it out again if you happen to miss it today. So we'll send it out in the follow-up email. And again, I want to thank everybody for attending, and happy Friday.